Okay, so welcome back. So what is the angular momentum equations? So as before that introduce, I would like to remind you, as you remember, the equation shown here is our linear transpose series, and for the momentum equations, actually we know that the B, what is the B? B is the extensive properties, and for the momentum equation, we know that the extensive property is the moment, is momentum. So this is equal to the mass multiply the v velocities, and we know that we have the b. What is the small b? The b is the intensive properties, and usually we teach you that the B divided the mass is equal to the intensity properties. So for the momentum equation, we only have the V velocity. But right now, we change. If we change the extensive property to be the mass multiply this is the force arm to the curve of the velocities, and then the B will become the force arms cross the velocity v. Okay, so this is our uh, new extensive properties, and the R is the force arm. Okay, and for the first one, this is for the momentum equations, and we know that the dB dt for the momentum equations is equal to sum of the force. And for the angular momentum equation, we know that the dB dt will equal to sum of the moment, because we have the additional force arm cross the velocity, cross the momentums, and then we have the sum of the moment. Okay, so now we know that the H system shown here is we call that is the M R vectors cross the V vectors, and the momentum change with retaining the control values. We still have the additional R vectors cross with the velocity factors. And there in the control surface also we have the R cross the velocity vectors. Okay, so this is called the angular momentum equations. And how can we apply the angular momentum equations? We try to see our problems include the rotations, motions, and then we need to apply the angular momentum equations. And you see, we are soon considering the uniform velocities, so we can replace the integration operators by the summations of along the contour surface. Okay, so actually the physical property is sum of the momentum for if sum of the moment is totally equal to the angular momentum's accumulations plus the angular momentum outflow minus the angular momentum inflow. So because our problem includes the rotation movement, so we will have some moment contributions. Okay, so we directly to apply the angular momentum equation to calculate the moment on a reducing band. So this is also the pipe band, but we change the different diameters in the inlet and outlet. And this pipe band is supported on horizontal axis through point A. So here we have the horizontal axis is our rotation axis along the across through the point A here, and our media is waters flow through the band at the discharge Q with the 0.25 meter cubic per second, and we know that the inlet pressures. So here we have the inlet pressure 1, and the P1 is equal to 150 kPa, and the outlet pressures here we have the outlet pressure P2. P2 is outlet, and the P2 is 59.3 kPa. And the total weight of our systems is 1.20 newtons, and X the 20 centimeters to the right of the point A. So the question is, please find the moment the support system must resist. So because this is the horizontal axis for the rotation problems, actually we have the flow inside the pipe band, and the pipe band should be rotated, right? But we have the support systems. We have the support system to overcome the rotation motions to fix the pipe band didn't move. And we know that some condition, the diameter of the inlet and the outlet are 30 centimeters and 15 centimeters. So we have a D1 for here is the 30 centimeters, so 0.3 meters, and the D2 is 0.15 meters. Since we have the D1, D2, so we can compute the cross-section area of the A1 is the 4 pi D1 squared. So use our calculator. This is the D1 is 0.3 multiplied 0.3 multiplied pi divided the 4. So the area is equal to 0.0706 meters squared. And then we have A2, again 4 pi D2 squared. Or D2 is 0.15 multiplied 0.15 multiply pi divided the 4. So this is equal to 0.0 meters squared. Okay, so for this problem, we would like to apply the angular momentum equations. So we know, based on the momentum equation, we know that the sum of the moment is equal to the angular moment change with the time inside the control volumes. But for this problem, we assume this is always the steady flow, so the angular momentum inside the control volume didn't change with the time. So we only have the angular momentum contributed from the inlet and the outlet. So we have the outlet flow velocity V2, and this is the inlet velocity V1. Okay, so we know that the outflow angular momentum minus the inflow angular momentums. So we have the S rate, we have the R2 cross the V2 minus the M rate plus the R1 cross the V1. Okay, this is our equation 1. And based on this equation, we still have some unknown parameters, such as the M rate. What is the M rate? The mass flow rate. And the questions already provide the discharge Q. And if we still have the density, then we can compute the mass flow rate very quickly. So this is actually equal to 0.25, and we assume the density is 1000. So we have 25 kilogram per second. The seconds, the two unknown parameters is the V1 and V2. So we know that we have the Q and the divided A1, so we have the velocities. And we have the V2, and we have Q and divided A2, and we have the velocity. Okay, this is based on the continuity equations. We know that the A1 V1 is equal to the A2 V2 is equal to the discharge. Okay, so we just directly to compute the V1 V2 individually. So the Q is 0.25 divided with A1 is 0.0706. So the velocity of the V1 in here is 3.54 meters per second, and the V2 is 0.25 divided 0.017. Is around to 114.7 meters per second. Okay, so we first compute the angular momentum balance. So we write down the M rate here, and we have R2 cross the V2 minus the M rate, R1 cross the V1. So first we have the M rate is the 250 kilogram per second, and we take a look. We have R2 Where is the R2? R2 is here. So we have the R2. Okay, R2 is the distance between here to the here. This is R2. And we have the R2. R2 is plus the 0.15 with the 0.325. And because our flow velocity is for the outflow is to the left, and the R vectors is these directions. So if you do the curls by your right hand, so in that way, this is the clockwise moment. So if the clockwise moment, so the moment is equal to the minus. So there is the minus 1 multiply the R2 is equal to 0.475. Okay, and the V2 is here is 14.7. This is for the angular momentum for the outflow side. And there is the inflow is the minus and rate is 25. And where is the R1? So we take a look. This is the center line for the velocity, and this is the velocity with the direction to the right, V1. And this is the R vectors, R1 vectors. And the distance for the R1 is here is 0.15 meters. And we do the cross by your right hand. So this is equal to the counterclockwise moment. Okay, so this is the positive moment. But there is already have the minus and rate. So the R1 is 0.15 and the V1 is the 3.54. So we can compute the answers is the 250 multiply minus 1 and then multiply 0.475 and then multiply the 4.7 velocities. Okay, so the first item moment is equal to minus 1745.6 and also minus the 250 multiply 0.15 multiply 3.54 velocities. So it is equal to the 132.75. So it's equal to minus 1878.4. This is unit is equal to the moment for the Newton meters. So this is for the angular momentum balance. And right now we consider that the sum of the moment. Okay, so first, what is the moment? The first one we have the pressures. we have the pressures contribute from the P1 and A1. This is the pressure force acting along these directions. And we have the R factor is the force arm factors for these pressures. So for this is equal to the moment is the P1 A1 and the distance is R1 is 0.15 meters. And because this is the moment, you can cross the R with the pressure force is the positive moment. Okay, and the second pressure in here, we still have the P2, A2, and also this is the R factors, and we use the R factors close to the pressure force 2 is also the positive moment. So there is the plus P2A2, and right now the R distance is the 0.15 plus 0.325. So there is 0.475 meters. Okay, and this is the moment from two pressure force, and we still have the weight. So this is the weight directions, and we have R factors. This is R factors, and this is the force weight directions. And by your right hand, you do the curls. So this is equal to the negative moment. So there is the minus the weight, and the R distance is 0.2 meters. 0.2 meters. And we didn't know the moment we need to support the system to resist. So there is additional moment A we didn't know, and we try to have the moment to fix the pipe bend didn't move. Okay, so we just calculate the moment, sum of the moments, and then we put the number inside the equations. So the P1 is the 150 1000s multiply the area is 0.0706, and the velocity is not the velocity, is the force arm is 0.15 plus the pressure 2. That is the pressure 2. The pressure 2 is 59.3 and 1000 kilopascals, and the area A2 here is 0.017, and multiply the force arm is 0.475, and minus the weight. Whether it's the weight is 1420 newtons, multiply the 0.2 force arm, and finally plus the moment acting on the rotation axis along the point A. So we use the calculator to compute the number each others. So 150 multiply 1000. This is a kilopascal. multiply the cross-section area 0.0706 and then multiply the force arm 0.15. So the first item, the number is the 1588.5 Newton multiplied meters plus the pressure 59.3 multiplied 1000 to be a kilopascal multiplied 0.017 cross-section area and multiplied 0.475 is force arm. So this is a plus the 478.85 minus the 1420 total weight multiplied 0.2 is the 2F4 annually plus the moment A. Okay, so we can compute the total value is 1588.5 plus 478.85 minus 284. So here is the answer equal to 1783.4 plus the MA. This is our equation 3. So we just put the answer. We have the 2 and we have the equation 3 to equation 1. Make the balance. So we have the 1783.4 plus the MA equal to the minus here 1878.4. So the MA is equal to the minus 3661. 3661.75. Okay, so it is quite close to equal to the answer right down in here. So, and this is the minus. So we know that the additional moment in here is the clockwise directions acting on the systems. So if we would like to support the system's most resist, so we need to have additional moment for the positive moment counterclockwise direction moment to fix the pipe band didn't move. Okay, so this is our final answers for this problem. So because this problem we are focused on the rotation problems. So if we would like to understand how large of the moment to support the system to resist, so we need to apply the angular momentum equation to calculate the moment. Okay, and the next problem is very famous. So if we have hydraulic power generators, we call that is Francis turbines, and this is very useful for the supply the power by the hydraulic properties. So we see the movie first. The movie just introduced what is Francis turbines. So Okay, so the, the animation showing here, usually this is very famous. We apply the hydraulic power generators, because we know that we have the water head in here, so we know that based on the Bernoulli equations, if we have the high water depth and we have a high velocity here, and then we have a high velocity flow inside here, and the water will push the runners start to rotate. So there is the inflow, and we have the outflow at the center runners, and the outflow waters will flow back to the environment. And then since the runner pushed by the water pressures, and then we will have the energy generators on the top, and we can deliver the power to other area have some power requirement site. Okay, so this is a problem also include the rotational problems. If we would like to understand how powerful and how large the power generated by these systems, we need to compute the moment first. And we have a moment, and if we know the rotational angles, that the angular speed, and we can compute how large of the powers generated by these systems. So usually we would like to compute the power for these generators. We need to apply the angular momentum equations to understand the moment first, and we know that the generators for the angular speed, so we have the omega values, and then you compute the two parameters together, we will have the powers. Okay, so what's the problems? You see that we also consider this is the Francis turbine, and we have a diagram shown here, and the water is directed by the guide fans. What is the guide fans? This is the guide fans. This is the guide fans, and as we mentioned, the video mentioned that we can adjust the angle of the guide fans to direct the waters, and the water is directed by the guide fans into the rotating runners of the turbines, so the water will push the runner, and the runner will start to rotate. And in this problem, we have the guide fans 70 angles from the radial directions. So this is the radial directions, and the fans, the angle between the guide fan and the radial direction is 70 degrees. The water is only with only a radial component of the velocity with respect to environment. So this is flow out, and the water will flow out along the center of the runners, and the outer diameters of the runner is 1 meters here, and the inner diameter is 0.5 meters. The distance across the runner is the 4 centimeters. This is the thickness of the runners. And we know that the problem for the discharge Q is 0.5 cubic meter per second, and the rotational rate of the runner is the 1200 RPM. The RPM is the revolutions, per minute. So we can convert the 1 to 0 multiply the 2 pi. Is 1 circle is equal to 2 pi radius, and 1 minute we convert to a seconds is 60 seconds. So including that, the unit will become to the radius per seconds, and this is equal to, use the calculator, 1 to 0 multiply 2 multiply pi, and divided the 60 seconds. So it's around 1.125.6 radius per second. And we know that the water density is 1000 kilogram per meter cubic. So please find the powers kW produced by the turbines. And we based on the power equations, we have the moment T, and we have angular speed omegas, and then we can have the powers. Okay, if you didn't know the why, we can follow this equation to compute the power, but if you remember, we can compute the powers from the force and multiply the velocities. If you change the velocity, this is the rotational actions, so the velocity can be replaced by the r omegas, and the r multiplied the force is equal to the moment, and this is the omega in here. So that's why we can multiply the moment by the omega to compute the powers. So the key questions here, we didn't know the moment t. This is our unknown parameters. So we need to use the angular momentum equations to compute the moment. So far, we need to write down the government equations for the angular moment equations. So sum of the moment is equal to the angular momentum in the control variable changing with the time. But for this problem, we assume this is a steady flow problem, so we don't have the angular momentum change in the control variable with the time. So we only have the balance for the inflow and the outflow for the angular momentums. But for these problems, we know that the rotation axis is on the runner centers. But for the outflow, it curves through the centers of the rotation axis. So for this problem, we don't have the angular momentums contribute from the outlet. We only have the inflow. So in that way, we know that for the inflow problems, this is the minus, we have the momentum rate, and the mass rate multiplied both factors close the V1 velocity. Right now, the V1 is our flow velocities for the inlet. Okay, so based on this equation, we didn't know the mass rate, the m rate, but we know that the m rate should be equal to the Q low density, right? The Q low density. So, but we have the Q and we have the rho, so we can compute the Q low value very quickly. Okay, so we know the Q is 0.5 and the density is 1000. So this is equal to kilograms per second. And we know that the Q. So how can we compute the V1 values? Okay, so we know that what is the V1. So we know the discharge is equal to the velocity factors dot product with the cross-section areas. Okay, but right now we know that where is the V1? The V1 is along these directions. Okay, it's along these directions, and we need to use the factor dot with the cross-section areas. So we know what is the areas. The area in here is the runner cross-section areas, and then we know the area in here is the right angles, and the right angle is equal to the radius circle length. So we have a diameter 1 meters, so the circle length is the pi d. The pi d diameter. Now the diameter is 1 meters, and the width here is 4 centimeters. So the width is 0.04 meters. So this is our areas. So use the calculators 0.04 multiplied by 3.14 pi. So this is equal to 0.126 meters squared. And what is the V1 dot with the cross-section areas? So the V1, we need to, this angle is 20 degree. So this is the V1. So this is equal to the V1 dot V1 multiply the cross-section area and with the cosine, with the sine 20 degree, because we need to project the velocity along these directions. These directions, radial directions, is parallel directions with the normal vector of the cross-section areas. Okay, so based on this equation, we know that the V1 value is equal to the Q divided the A sine 20 degree. Okay, and the Q is the 0.5, and the area is 0.126. Multiply the sine 20 degree. Okay, so we can compute the velocity based on this formula 0.5 divided the area 0.126 and divided the sine 20 degree. It's the velocity equal to 7.6 meter per second. Okay, so right now we have the velocity and we have the mass flow, so we can go back to the equations. So this is equation 2, this is equation 3. So, and we know that the sum of the moment is equal to t. So we have 2 equation, 3 equation, and put back to the equation 1. And we know the sum of the moment only have the t moment contribute from the distance, and there is the minus, and we have the mass flow rate is the 5 to 2, and but right now we need to process the cross with the v velocity. Okay, so we go back to see here. This is sorry. this is the inner flow, so we need to project the flow with these directions perpendicular to the radial directions, and we have a force arm. The force arm is the radius of the runners. This is our force arm. Okay, so the force arm is along these directions, and we do the cross cross vectors close to the velocity vectors. So it is the clockwise directions. So in here we have the additional -1 because the moment is clockwise. It's negative moment, and the r is the radius of the runner. The radius, the diameter is 1 meter, so the radius is 0.1 meters. And we need to project the velocity to along these directions is perpendicular to the radial directions. So we know the velocity is in this direction. So if we would like to project to these directions, we need to multiply the cosine 20 degrees, and the V1 is the 11.6. Okay, so we can compute the moment is the 500 multiply the minus and the minus, so it's a positive. So we directly multiply the 0.5 and then multiply the cosine 20 degrees, and the velocity is 11.6. So here we have the positive moment is 2725 2725.1. This is Newton meters, and we compute the power is T omega. So V2725.1 multiply the omega in here is 125.6. So the answer is equal to 34273.6 watt. Okay, so it's around the 4343 kilowatt. So this is our final answers. Because the problem is related to the rotation problems, and this is the very famous hydraulic power generators. So if we can find the solution for the moment of the systems, and we know that the angular radial speed omega, so we can estimate how large of the power generated by these systems. Okay, so this is very useful if we can apply the angular momentum equations. It's very useful to predict the power, okay, for these problems. So based on these chapters, the next semester will have the laboratory experiment related to the fluid jet. So this is the problem for the fluid jet, and you see this is the jet, and we'll have the fluid drop outside to push some object, and the object will connect to the mass recorders. They will supply the mass, how large mass contributed from the fluid jet. So we have we just take a table summarize. Actually, we can control the discharge, and based on the discharge equations, we already know the cross-section areas, and we can adjust the different discharge. So we can also control different speed of the fluid jet U, and based on the Bernoulli equations, we know that this is the initial fluid jet speed, and if the fluid is jet to upward for these locations, this is the U and this is U zeros. So we know that based on this equation, we can calculate how large of the U zeros. And since we have a U zeros, so we can compute the force based on the momentum equations, though Q U zeros. And we have a recorder also supply the mass, how large of the mass contributed from the fluid jet, and we can compute the theoretical force, and we can compare the measures and the theoretical each other to make the discussions. So this is the laboratory experiments related to the momentum equation ideas. Okay, so next semester you will have this practice, try to understand the physical meanings, physical properties from the momentum equations. Okay, so today we stop here, and next Monday I will also introduce the momentum equations for a differential form. As I teach you the continuity equation for the differential form right down here. So for the momentum equation, we still have a differential form, and I will teach you how to derive the momentum equation for a differential form. OK， 好，那我现在稍微说明一下下礼拜一可能会考的这个题目方向。那当然我们一定会去考这个有关于 momentum equation 的应用。那我可以跟大家提醒，我们一定会考的是火箭的问题。火箭的问题包含怎么去推导火箭最后的这个匹配方程式。我们说火箭最后匹配方程式可以写成现在这个样子。那我们有这个匹配方程式，我知道一开始火箭的质量，我知道最后火箭的质量，那我知道一开始的这个推进力的大小，那还有它的这个 mass flow rate， 我是不是就可以去估计在怎么样的消耗掉多少的这个质量的，用这个 ratio 来表示，我可以得到多少的上升速度，火箭的燃烧的上升速度。那为什么我们会有这个方程式？那它是怎么推导而来的？大家记得我们一开始的推导方式都是 follow 这个 momentum 的 equation， 然后在这个过程中，我们在推导这个 follow 的 momentum equation， 大家记得我的观察的物件是不断的在加速的，所以我要怎么去算这个出流的这个速度相对于这个惯性坐标？那这个问题的惯性坐标我们是锁在地面上，那这个就是它出流的 velocity， 出流的 velocity 是喷射出来的气体速度相对于这个减掉这个火箭的上升速度，那就是我们的出流的速度。所以整个方程式才可以写成这个样子。那在这个地方，其实我们在 control volume 里面的质量是有变化的，所以这个 item 不能忽略掉，因为火箭的气体一直在燃烧殆尽，直到殆尽这样子。然后我们推导的过程中也发现说，我们可以运用连续方程，把这个东西展开以后，有些项次是可以等于0的，最后就可以长成这个样子。 然后我们又忽略掉 jack force 跟 weight， 所以最后只剩下 thrust force 会跟这个有关系。那我们假设火箭里面的质量其实随着时间的变化可以表达成起始的质量减掉 moment 这个 mass rate 减掉发生了多少乘上发生多少时间。那我们把这个 mr 带进去这个方程式，那我们就可以去求解最后的这个火箭上升速度跟什么样的参数是有关系的。这个大家一定要会，一定要会。我们下礼拜一一定会去考这部分。OK， 那相关的小考说明，请大家再多注意一下。希望在第4次的小考，大家就不会有这些上传迟交的问题。好，那今天我们的课程就上到这里。